All right, now that you have had the opportunity to investigate the graphs of secant and cosecant and tangent and cotangent a little bit in that Desmos activity, and if you haven't done that Desmos activity, pause this video and go do that Desmos activity. But now that you've gotten to explore those a little bit, I would just want to highlight a couple of the really important characteristics that I think are important to have written down about what these functions should look like. So I think that actually knowing these techniques are going to help you be able to recognize which function is which, being able to reason through rather than just memorizing things. So, okay, so here are a couple of things that we learned in those Desmos activities that I want to just highlight a little bit. We saw that all four of these other functions, tangent, cotangent, and secant and cosecant, they're all periodic functions, just like sine and cosine were periodic functions. But they might have a different period. So remember that the period of a periodic function is the length of time that it takes for the function to repeat. And secant and cosecant have period 2 pi. So that was just like sine and cosine. So it took a distance on the x-axis of 2 pi, so 6.28 something, 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 to start the repetition. Whereas cotangent and tangent had a shorter period of only pi. So it took half the time to repeat. Okay. I also want to be able to talk about the domains of these functions, and a nice way to be able to remember them is actually using the quotient and the reciprocal identities. So the domain of a function, remember, is in this case, it would be the theta values, the angles that we could plug into a function. And when we're thinking about graphing these, we're thinking about theta actually on our x-axis. We can use any independent variable, and we tend to use theta for angles. So cosecant is 1 over sine theta, right? And cosecant is going to be undefined, right? We'll have domain restrictions whenever we are dividing by zeros. So whenever really sine of theta is equal to 0, because we would divide by 0. So to know the domain restrictions of cosecant, we need to think about when sine would actually be equal to 0. So I'm going to quickly sketch that. And this is why it's so helpful if you can just kind of commit to memory the general shape of what sine looks like. We can remember a lot of information from it. And this reminds me that sine, it's the one that touches at the origin. So sine is 0 whenever at numbers like theta equals 0 and theta equals pi and theta equals 2 pi and 3 pi and so on. And also like negative pi and negative 2 pi. So we have domain restrictions when theta is 0, pi, 2 pi, dot, 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 or maybe negative pi or negative 2 pi or dot, dot, dot. Okay, and then our secant function also has some domain restrictions. And we'll remember that secant is 1 over cosine theta. So cosecant is going to have some domain restrictions whenever cosine is equal to 0. Excuse me, cosine theta. And if I quickly just remember what cosine looks like, it's, well, that was bad. Ooh, kind of like this, right? It starts up and then down. And its zeros are things like pi over 2 and 3 pi over 2. And 5 pi over 2, and so on. So i.e. at theta equals pi over 2, 3 pi over 2, 5 pi over 2, dot, dot, dot. And also things like negative pi over 2, and negative 3 pi over 2, and negative 5 pi over 2, dot, dot, dot. Right, but if you just know this information about the graphs of sines and cosine, and you know the reciprocal identities, then you don't need to memorize this new information about the domain restrictions of cosecant and secant. You can just use what you know about sine and cosine to figure that out. Okay, and then let's see, tangent theta is sine theta over cosine theta. So we would be dividing by 0 whenever cosine theta is equal to 0. Right, and I already know that list, so I'm just going to copy and paste it here. So i.e. that happens. Copy, paste, fantastic. Those same values, right? Those are my domain restrictions for tangent theta. And cotangent theta is cosine theta over sine theta. So it'll have domain restrictions whenever we would be dividing by 0, whenever sine theta is equal to 0. So when sine theta is 0, and i.e. that's at things like negative 2 pi, negative pi, 0 pi, 2 pi, and so on. Right, and that's just going back to my graph of sine up here. Right, and every single place we have a domain restriction, then we're going to have a vertical asymptote. Right, we cannot have graph if we have a domain restriction. And so for these functions in particular, that's where we're going to draw these vertical asymptotes, is at those angles that we've drawn. And then we'll have the graph between them. So for secant and cosecant, it'll look something like this between those, and tangent or cotangent, it'll have more of my loops, and we'll talk about those in a second. But I think that's a great starting point to remember what these look like. Okay, then we should think about the range, and let's see. Actually, let's think. I'm gonna show you the graphs to refresh your memory, and then maybe we'll talk back about what the ranges are, because I think it's easier to remember that from the graph itself. The x-intercepts of each function. Let's see. An x-intercept is going to happen whenever my thing is equal to 0, right? When my y value is 0 is when I have an x-intercept. And let's see. Secant theta, remember that's 1 over cosine theta, and cosecant theta is 1 over sine theta, right? And so if I were going to have x-intercepts, I would need like this thing to be equal to 0 at some point. But remember that when if a fraction is equal to 0, then it's actually like the numerator equal to 0. And my numerator is always 1. So I'm never going to be able to get 0. I'm always doing 1 divided by a number. So I can't get 0. Because so I would say maybe that we don't have an x-intercept because the numerator of these is always 1. Another way to think about it is because sine and cosine are always defined as they're never undefined. If we would do 1 divided by an undefined, is sometimes actually when we would get 0 as our answer. But they're always defined as a whole number. So we would never have a 0 answer. And we'll see that in the graph that we actually will never touch the x-axis here. Tangent and cotangent, let's see, tangent theta, and I always go back to the definitions here, that tangent is sine theta over cosine theta. So tangent theta is going to have x-intercept whenever my numerator is equal to 0. So whenever sine is 0. So tangent is when sine theta is 0, which we've already talked about earlier on the page, right? That's pi, 2 pi, negative pi, so on. And for cotangent theta, it's sine over, no, it's not. It's cosine over sine. And so these are going to have x-intercepts when the numerator, cosine theta, is 0, which is things like pi halves, 3 pi halves, 5 pi halves, and so on. So that's what I expect when I look at these graphs, and let's double check. So here I have, let's look at just tangent and cotangent and look at those properties. So if I look at my x-intercepts, that's what we were just discussing. We have x-intercepts at 0 and pi and 2 pi and negative 2 pi, which is the same place when sine is equal to 0. So that matches what we just said. And our cotangent has x-intercepts at things like pi halves, negative pi halves, 3 pi halves, and so on. Okay, if we also look at our domain restrictions, and actually maybe I did a bad sketch here. We probably should have had for all of these, go ahead and the best interpretation of these graphs always have our vertical asymptotes here lined in as well. These are not very perfectly straight lines, but they're supposed to be. And we normally do asymptotes, remember, with a dashed line, so that's what I'm doing them with here. But what we can see is that for tangent, we have our domain restrictions. We have our vertical asymptotes at 3 pi halves, 5 pi halves, so on, like we just said. And for cotangent, we have our vertical asymptotes, our domain restrictions at the multiples of pi, right? That's what we had set up here. Cotangent at multiples of pi. Tangent has its vertical asymptotes at all the halves. Okay, and then maybe let's think about our range. And I see that even just one cycle of this, I have y values all the way down and y values all the way up for my tangent. And cotangent, I have y values all the way up and all the way down. So for both of these, the range of my graph is going to be negative infinity to infinity for the range of tangent and cotangent. Okay, then if we look at our secant and cosecant graphs, let's first check that we don't have any x-intercepts, right? So note, no x-intercepts. We do have some domain restrictions. Here for secant, we have them at the pi halves, 3 pi halves, negative 3 pi halves, all those. And really every time you sketch in these functions, they should be there. And for cosecant, it's at the multiples of pi. Again, these are supposed to be straight lines, but I'm doing my best here quickly. Okay. And that matches what we had here. We said that cosecant is going to have domain restrictions at all the multiples of pi. And that's what I'm seeing down here. The multiples of pi is where I have my domain restrictions. Okay, now let's think about the range. Let's say for secant first, I see that I have some y values up here. So I'm going to get maybe, I think this value here is 1. So I have y values from like 1 up, and I also have y values like from -1 and down. But I'm actually missing, there's no graph kind of in this middle area. And the same thing is true for cosecant, that I'm missing that middle area, but I have larger values and all the negative values as well. So for both secant and cosecant, then I would say that my range is negative. Let's fix that. I would say that my range is negative infinity to -1 inclusive, and then union 1 to infinity. If we saw that in a number line, it might look something like this. We're filling in this area, we're including 1 and -1, and filling in that area. Okay. One trick that I like to use to just remember which one is which. Let's see, for tangent and cotangent, this is where I just have a mnemonic device and I just remember that tangent goes up. I don't know how to remember that, except for that tangent is up. You might also remember that like in quadrant 1, tangent, well, that's not even a good way to remember it. I just remember that it goes up. I don't know, I don't really have a good memory trick there. There are ways to think through it, but it's probably a little bit too complicated. It's probably easier to just remember that this one goes up and cotangent goes down. For secant and cosecant, I remember the fact, and you probably saw this in your Desmos thing, that like the sine or cosine graph actually touches at these points. So what I like to do is I like to sketch in the sinusoidal graph that like touches at all of those points. Right, and this is just a sketch to remind myself, and I say, oh, well, on the right-hand side, what I just drew in is sine, and so this one must be cosecant because it touches at the graph of at the mins and maxes of sine. Okay, and likewise, secant and cosine touch at the mins and maxes. So secant and cosine x touch at the mins and maxes. And I just remember that, well, secant and cosine, they go together, they're reciprocals, and cosecant and sine, they go together, they're reciprocals. So that's kind of a memory trick for that as well that I think is really helpful.